Alright, welcome back. What we're covering in this video is what's called total internal reflection. Now, it may sound complicated, but you'll find that it's really simple. The things you need to know before this video is you need to understand what refraction is, what the phenomena is, and you need to know what the index of refraction refers to. So what we'll be covering is defining total internal reflection and then determining something called the critical angle. So previously, if you've seen the other refraction videos, you know that we've focused a lot on the incident ray, the refracted ray, the incident angle, and the refracted angle. Now, I haven't mentioned too much about this arrow here, which is the reflected ray. So what we're going to do is focus on this one for a little bit. Here's a PhET simulation that you've seen many times before. And what I want you to do is focus on this ray over here. This is the reflected ray. Anytime a ray of light hits a new medium, some of the light will reflect. Now, we haven't focused on that at all before. We've only focused on the light that refracts. But what you need to know moving forward is that some of the light reflects. What you may notice about this reflected ray is that it's pretty dim compared to the other two. Now, as I increase the incident angle, at a particular point, the refracted ray gets a lot more intense. It's no longer as dim as it was before. What this represents is that more light is being reflected. So here, not so much light is being reflected as compared to here, where a little bit more of the light's being reflected. Now what I'm going to do is I'm going to change the mediums from air to water. I'm going to just swap it so it's from water to air. And I want you to notice that the same phenomenon happens. The ray of light comes, reaches a new medium, and some of it is reflected. It's a dim light. Now as I move down, the light gets a lot more intense. But what I want you to notice is what happens to the refracted ray as I increase this angle. So right there, the refracted ray no longer exists, and the reflected ray is where all the light goes. Let's see that one more time. So here I have an incident ray reaching a new medium and bending. Some of the light bounces off. As I increase the incident angle, more and more of the light is bouncing off. And when I say bouncing off, I just mean reflecting. And this line is getting more intense. At a particular angle, right here, all of the light reflects and none of the light refracts through. So what I've written is that what we notice is that at a particular angle, at a special angle, all of the light reflects within the medium. Here's a little picture showing a similar thing. A laser is being shined. It enters water, and then it reaches the boundary between air and water. And none of the laser goes through as you'd expect it to. All of it bounces off this boundary and just reflects. Now I'm just going to underline a few of these words in the sentence. All of the light reflects within the medium. All of the light, another way to say that, is total. And because the light is reflecting, we say reflection. And the light stays within the medium, so internal. So what we call this phenomena is total internal reflection. Now I'm just showing you this so that you could break it down into the little parts so that you know what each part means. Total internal reflection just means that the light is reflecting within the medium. It's staying within the medium. Now here I have a diagram that's very similar to our refraction diagrams that we've seen before, but what is important is to know that this top medium here is less dense than the bottom medium here. So what it says in the text is that total internal reflection will only happen when the first medium has a higher index of refraction than the second medium, and the incident angle is greater than the critical angle. Let's focus on this first bit here. It says the first medium has a higher index of refraction than the second medium. That's the first condition for total internal reflection. Going back to our simulation, just to prove to you that this is true, if I go from a less dense medium to a more dense medium, there is no angle at which total internal reflection will occur, because it only happens when you go from a more dense material to a less dense material. So let's go from a more dense material to a less dense material. Let's switch it up to water and air like we had it before. And now total internal reflection does occur. Now another thing I want you to know is that at this special angle, total internal reflection will occur, but also any angle above that angle will also result in total internal reflection. So at this special angle here is the minimum angle for total internal reflection. Any angle above it will still result in total internal reflection. But this will only happen if you're going from a denser medium to a less dense medium. In this diagram, we're going from a denser medium to a less dense medium, and that's why it's bouncing off. Let's talk about the incident angle now. What it says is that the incident angle has to be greater than the critical angle. The critical angle is defined as the angle past which total internal reflection will occur. So in this example, that very special angle where it starts to happen, right here, 48.7 degrees, is what we'll refer to as the critical angle. 48.7 degrees is where the light will start to totally internally reflect, and that special angle is called the critical angle. Now, to solve for the critical angle, the equation is given as sine theta c, and theta c is what we'll call the critical angle, that's the symbol for that, equals n2, the index of refraction for the second medium, over n1, the index of refraction of the first medium. Now keep in mind, total internal reflection will only happen when you're going from a dense material to a less dense material. So your N2 will always be less dense than your N1. Okay, N1 will always be a bigger number than N2 if you're talking about total internal reflection and finding the critical angle. Now there are two examples here, and I want to solve them both. First example is find the critical angle for a water-air boundary. The index of refraction for water is 1.33 and 1.00293 for air. So they want to know what is the critical angle for this boundary. Anytime you're asked about critical angle, you already know its total internal reflection, and they want to find theta c. So just writing down the equation, sine theta c equals n2 over n1. Now, this is a water-air boundary. It's not mentioned whether it's going from water to air or from air to water. But because we're looking for a critical angle, we know that it has to go from a denser material to a less dense material. That's how I know it's going from water to air. So water will be my N1 and air will be my N2. Sine theta c equals N2 is for air, and N1 is for the water, 1.33. Now, pull out the calculator. This equals close to 0.752. 0.752 is sine theta c. Again, this is not the end. We don't care about sine theta c. We want to find theta c. So we have to take the sine inverse of this value. Sine inverse of 0.752 is 48.7 degrees. 48.7 degrees. So, between water and air, if you shine your ray of light 48.7 degrees with the normal line, you will get total internal reflection. Now, it's not a coincidence that that's the angle that we have here for water and air because that's the critical angle. So I've just solved for it to show you how we reach that number. Now keep in mind, if the angle is any greater than this number, you'll have total internal reflection. This is just the minimum number. Example 2. A ray of light enters flint glass from water with an incident angle of 20 degrees. Will total internal reflection occur? So we have a ray of light going from flint glass, to flint glass from water, and it has an incident angle of 20 degrees. Now what they want to know is if total internal reflection will occur. The conditions for total internal reflection are if the first medium is more dense than the second medium, and if the angle is greater than the critical angle. So what we have is a ray of light entering flint glass from water. So here's my water, here's my glass, and here's my angle of 20 degrees. Now, will total internal reflection occur? Is my first medium more or less dense than my second medium? Water has an N value of 1.33 and glass has an N value of 1.66. Now, I'm taking a long time on purpose so that you can get to think about this, but because water is a lower index of refraction than glass, there will be no total internal reflection. So the answer here is no, total internal reflection will not occur because the first medium has a lower index of refraction than the second medium. Now let's check to see if you've understood. Pause the video here and try to answer these on your own. The first question is, what is total internal reflection? What is the phenomenon? Describe the phenomenon as best as you can. Second is, what are the conditions that must be met for it to happen? Third is, describe what is the critical angle. What does it refer to? What does it mean? And number 4, how do we calculate it? Summary of the video is right here. First thing, total internal reflection is when all of the light reflects off of the medium boundary. Number 2, it only happens if the first medium has a higher index than the second and if the angle is larger than the critical angle. The critical angle is the angle at which a ray of light will begin to totally internally reflect, and to solve for it, the equation is given as sine theta c is equal to n of the second medium divided by n of the first medium. Keep in mind that anytime you're above the critical angle, you will totally internally reflect. The critical angle is just where it will start to do it. It's the minimum angle where total internal reflection will occur. I've said totally internally reflect and total internal reflection about 100 times this video. If you have any questions, put them in the comments. Otherwise, thank you for watching.